So, let us continue the discussion with the design now. So, we have looked at different kind of propeller and how they look like, their nomenclature. Now, we will go down to slightly different aspect of it, like how aerodynamically these are designed. So, let us look at the aerodynamic design, and that is done through different theory. So, let us start with the actuator axial momentum theory, or so we will start with axial momentum, or this is called actuator disk theory. Okay. So, we will start with that. So, actuator disk is also sometimes denoted as this actuator disk, also called the Rankin-Froud or slipstream theory. So, these are different naming which are given. So, this theory based on 1865. So, the actuator disk theory replaces the propeller with the infinitely thin plane or actuator disk. So, let us see how it can be done. Let us draw some configuration here. So, let us say this is the actuator disk sitting there, then the flow could be like this. Could be like this, then this goes like this. So, let us say this is the actuator disk sitting there. Now, this is 1, so that is 2, this is the disk, this is T 3, so this is a stream tube. So, that is 4, and if we plot this, so now this could be V, then this is V 1 plus A, V 1 plus B, this is velocity, then we can see the similarly pressure, this is P A, this is P 2, this is P A, so this is P 3. So, and if we plot that in a slightly 3-dimensional way, then it looks like here is the disk sitting there, and so this is what V 1, P 1, let us say this is area A 1, this is 2, 3, so P 2, P 3, A 2, B 2, B 4, P 4, area 4, 4. So, that is a thin disk kind of, now which imparts a certain momentum to the fluid passing through it when there is this actuator disk. Now, this theory provides an initial idea regarding the performance of the propeller and also its efficiency, but it cannot provide you the detailed design related aspect. So, there are certain assumptions in this particular approach. One is the fluid is one dimensional, incompressible, compressible, then perfect isentropic. Second, flow has uniform properties across the, that is velocity and pressure, across any plane normal to the flow except for the discontinuous jump in pressure across the disk itself. So, uniform property, that is another. Third is the rotation neglected, that means the rotation important to the flow is also neglected. Fourth, the streamlines all the edge of the disc define the outer limit of the contracting stream tube, which passes through the disc and separate it from the surroundings. Okay. So, that means the stream tube provides the boundary. So, and the stream tubes also has cylindrical section in both for stream and for downstream. And then fifth is the flow outside the propeller stream tube has constant stagnation pressure, no work is. So, outside propeller stream tube has constant stagnation pressure. So, this particular diagram provides you some pressure velocity diagram. So, one is first stream here, first stream from the propeller, 2 is just in front of the propeller. So, let us say 2 is here, then 3 is here, which is just after the propeller, 4 is again further downstream of the propeller. So, the distance between 2 and 3 is infinitesimal because the disc is thin and this is what is assumed to be. Now, also the stream tube, along the stream tube sections 1 and 4, the velocity increases from the free stream value of V1 at cross section area A1 to the area A4 and V4. So, the static pressure at station 1 and 4 could be P1 and P4, so which are atmospheric. That means P1, P4, it would be P atmospheric. But the pressure difference across the disc is built up, and so what we can write, so velocity at disc we can write V2 equals to V3. So, which is written as V2 equals to V1 1 plus A, where A V1 is V2 minus V1 is the increase in velocity through the disc, where A is called the axial inflow factor. Okay. So, now if we have fully developed slipstream, the velocity V4 is V1 into 1 plus B, where B V1 equals to V4 minus V1. So, that is the increase in velocity there, and B is called the slipstream factor. So, what we can get that A is V2 minus V1 by V1, B is V4 minus V1 by V1. So, we can estimate the thrust. So, we can apply Newton's motion, and there is a region, control region between 1 and 4. The thrust could be m dot V4 minus V1. Now, let us say if we drop the subscript on the free stream velocity V is V1, then we can write this one is m dot V into 1 plus B minus V, which is m dot B V. Now, here m dot is the mass flow rate or mass flow through the actuator disc, through the actuator disc. And also we can write that m dot equals to rho a V 2, which is rho a V 1 plus A. Now, when I plug this back together, so this will give me rho a V 2 V 4 minus V 1 rho a V square 1 plus A into B. Now, force balance across the disc require that it would be A into delta P. So, this is from that figure that we have drawn, and where delta P would be P 3 minus P 2. Now, if we eliminate T, we get delta P equals to rho V square 1 plus A into B. Now, we have assumed the flow is incompressible. So, the Bernoulli's equation applied between, now we apply Bernoulli's equation between 1 and 2, we write P A plus half rho V square, P 2 plus half rho V square into 1 plus A square. Now, similarly, we apply the Bernoulli's equation between 2 and 3 and 4, that gives me P 3 plus half rho V square equals to P A half rho V square 1 plus B square. So, what we get that P 3 minus P 2 equals to delta P equals to half rho V square 1 plus B square minus half rho V square, which will rho V square B 1 plus B by 2. So, that is what you get as delta P. Now, if we eliminate delta P from this equation and this equation, we get 1 plus A equals to 1 plus B by 2. So, that means A equals to B by 2 or B equals to 2A. So, one can prove that B 2 would be B 1 plus B 4 by 2. Now, if you have no forward velocity, or rather 0 forward velocity, so B V 1 equals to 0, then V 4 equals to 2 V 2 when the forward velocity is 0. So, this looks quite simple, but Important result means that any speed including 0, one of the final increase in velocity in the slipstream has already occurred at the rotor itself. So, now going back to that thrust expression, where we have written T, which is rho a v square 1 plus a 2a, which is rho a v square 1 plus b by 2 b. Now, this equation is an quadratic equation. So, if we solve, after solving, what we get, a equals to minus half plus minus half square plus t by 2 rho a v square. Now, let us say small v, if we say this is induced velocity at the propeller disc and can be written at a into v, then what we get, that small v equals to a v minus v by 2 plus minus 2 square plus t by 2 rho a. Also, we get b equals to minus 1 plus minus 1 plus 2 t rho a v square. Now, again we will denote w equals to b v, and this one is the induced velocity for downstream the propeller disc. So, this is b v minus b plus 2 t by rho a. So, we get all these details that we wanted to calculate. So, now we can look at some other factors like propulsion efficiency or propulsive efficiency. So, that is eta p, and that is defined as P A by P, which is T V by P, and where P A is the thrust power or useful thrust power, which is T V. This is the, or sometimes called the available power, and this is the P is the power delivered. So, this is a ratio between available power to the power delivered is the propulsive efficiency. Now, for the actuator disc model, this efficiency is an ideal propulsive efficiency, because it ignores all losses except the associated streamwise kinetic energy. So, what we have, the useful power is T v, which is rho a v cube 1 plus a into 2 a. Now, the power expended on the air, which is also P, which is also rate of change of kinetic energy. Okay. So, that becomes half m dot v square 1 plus b square minus v square, which is rho a v cube 1 plus a whole square 2a. So, this ratio of these two powers for the ideal actuator disk model is called the ideal Froud efficiency, that is eta f, that is ideal Froud efficiency, and this is 1 by 1 plus a, which is ratio between v plus. So, this proves that higher efficiency of propulsion can be achieved by large rotor with very small increase in the fluid velocity. So, achieving thrust by large surfaces rather than velocity. So, ideal Froud efficiency eta f is always greater than actual propulsive efficiency. So, that is what it is always like that. Now, we will go to another theory which is called the simple vortex model. So, this is a sort of an modified actuator disk. Now, a practical assessment of the propeller performance and the design. So, we can consider a stream tube that passes through a radius r and which is shown here. So, there is a propeller disc and there is a stream tube. The corresponding angular speed at this blade is, let us say, angular speed, that is omega r. So, this is the angular speed of the propeller, r is the local radius of the propeller. When fluid passes through this propeller, through the propeller section, it acquires an angular speed due to the swelling, because this is called so-called simple vortex model. So, then the rotational speed at the propeller section would be u, which is a omega omega r, where a omega is the angular induced factor. Okay. So, the local flow velocity just downstream of the propeller can be estimated, which is like, let us say, V r, which is equals to V 2 square by u square, which will be V 1 square 1 plus a square plus a omega omega r square, square root of that. So, the local flow velocity for downstream. So, the local flow velocity for downstream of the propeller can be found as V r prime. So, which is root over of V 4 square plus u square. So, we can write that down as V 1 square 1 plus b square plus e omega omega square. Now, that is what you get So, this is where the VR and U and V2. Now, the let us say the at radius r, the local propulsive efficiency, based on modified momentum theory. This is the, so this is called the modified momentum theory, or this is what exactly the simple vortex theory. So, sometimes it is called the modified momentum theory or simple vortex theory. So, based on that, the eta we can define as T V1 by T into V1 plus kinetic energy of the losses. So, which we can write that m dot V4 minus V1 into V1 m dot V4 minus V1 into V1 plus half m dot B square V1 square plus U square. Okay. So, this one can be further simplified, and one can write this could be B V1 square. So, you can do this math, B V1 square plus B square V1 square plus U square by 2. So, what we can write is 1 by 1 plus B by 2 plus U square by 2 B V1 square, okay, which one can write 1 by 1 plus A plus U square by 4A V1 square. So, finally, this one if we replace it back, then we can write that, let us write it here, that eta equals to 1 by 1 plus A plus E omega square r square by 4A V1 square. So, this is what one can get with the modified momentum theory or simple vortex model. So, you can see that either one can do the analysis with like an actuator disk theory. This is one of the simplest way one can do the design, simple vortex model or modified momentum theory to get this efficiency and other stuff. So, there are two different way you can look at it. These are the again the simple theories which are used to calculate this actuator disk analysis, but these are again assuming that disk to be thin and then carrying out this analysis. But one can always look at these blades and the detailed analysis, either put it in the wind tunnel or somewhere by doing testing, or sometimes doing the computational approach where you can calculate all this numerically and look at the flow field around it. So, we will stop this theoretical discussion here, then continue some of the part in the next class.